Hey everyone, FPS Chazza here. Welcome back to my nuclear stuff series. So today we are covering charged particles. We've covered the intro to particles and some basic radioactive mechanics. I think now we're ready to actually get into some radioactive particles today. So we're going to start with charged particles. Now that we've covered that stuff, we can now discuss this stuff. So radioactive decay is the process through which unstable atoms become stable by releasing excess energy, which is called radiation. This excess energy is released in the form of at least one particle, which will be discussed in this video. There are many kinds of radioactive particles, but we're only concerned with 5, which fall into one of 2 categories: charged particles and neutral particles. So this video will be charged particles, and then there will be a separate video for the neutral particles. The charged particles consist of alpha particles and beta particles, and the neutral particles consist of photons, neutrons, and neutrinos. 3 of these we explicitly discussed in the particles video: photons, neutrons, and neutrinos. One we implicitly discussed: beta particles. So let's move on to beta particles. I'm just going to do a little squiggly. I can't draw this too quickly, otherwise the ink kind of just blots out. So beta particles, and no, we're not talking alpha and beta like red pill. We're talking beta particles. Okay. So we talked about this in the first video. Actually, beta particles are electrons. I'm not sure if I mentioned this. I may have. So let me read my script instead of trying to wing this here. So there are 2 beta particles, and they're both electrons. However, electron is a general term that encompasses 2 particles. So we have these 2 particles, and they're both electrons. But electron is not. That's just a generalization, if you will. So the electron that I've been talking about, the -1 charge, is actually a negatron. So this is the electron that everyone thinks about. There's another one. This is the antimatter variant with a +1 charge. This is a positron. Has exactly the same mass, exactly the same properties, except it just has an opposing charge, and it's made of antimatter. So if these 2 were to come together, they would annihilate. You may have heard about the antimatter-matter annihilation effect before. So if these 2 guys come together, they'll annihilate. That's another way to produce gamma particles. More into that later. So the negatron, as you might be able to guess, is the beta minus particle, and the positron is the beta plus particle. So these guys will also encounter that same electromagnetic interaction effect of alpha particles that causes them to slow down. Electromagnetic. Okay, we'll go with that. So beta radiation is generally considered the second strongest. Gamma is the strongest, beta is second, alpha is the weakest. That has to do with the penetrating power, but if alpha gets inside of you, it's the strongest. So for our purposes, just consider gamma, beta, and then alpha as strongest to weakest. So about a few millimeters thick, something like this thin of aluminum will stop beta particles. So they're a little more penetrating than alpha. You got to worry about this if you're just a human out in the elements. You don't have enough dead skin cells to stop beta particles, so they will do some damage to you just sitting like this, but that's only if they're sitting out in the air, just like giving your little goo pile from before. I don't know. If they're sitting out in the air like this, then yeah, you got to worry about it. If you're talking about some little like nice radioactive source in a big steel drum here, then you might as well just forget about the beta particles. They're not doing anything to anyone. They're all going to get shielded by that steel in there or whatever. So since the beta is a lot smaller, you don't have that discrepancy like with alpha, where if it's like outside of you, it doesn't do anything, but if it's inside you, it's like, holy crap, death. And that is because the beta particle is the electron. Like in that other video, we said an electron is 1/2000th the mass of a proton. Well, an alpha particle has 4 protons, basically. 2 neutrons, 2 protons, which are about the same in mass. So that means the beta particle is 1/8000th the mass of an alpha particle. So yeah, it doesn't have as much, raw punch in terms of like damaging DNA or something like that, but it's more penetrating. Beta radiation is not from, let's draw ourselves a nice nucleus here and some electrons. And I always end up drawing helium. Don't worry about it. I guess it doesn't really work for this example, but we'll just go with it. So beta radiation is not just, it's not due to a shell electron being kicked out. That's not what beta radiation comes from. It's just an energy imbalance in the nucleus, and the nucleus ends up kicking out one of these things to try and balance some energy here. So, as from before, we have the beta minus particle and the beta plus particle, the negatron and the positron. So, the two beta minus and beta plus emissions affect the nucleus and the resulting atom in different ways. So, if we have a beta minus emission, so beta minus is a negative particle, so we lose a -1 charge. So then in that case, it makes sense. Well, hold on. So the electron isn't just like, kicked out of the ether. One of these particles in here gets changed to something else to kick out a beta particle. So we're talking beta minus. So that means we get an electron kicked out of the nucleus. So this means we have a neutron just decaying into a proton. So we have a neutron that just got turned into a proton in the nucleus. So the way I like to think of this is the neutron is 0 and the proton is +1. So a good way to think of the neutron is +1 -1. So if the -1 goes out, then you're just left with +1. So that becomes a proton. So that's a good way to think about that. And then in addition to that, you get the resulting proton. Let's get this here. So we start with the neutron. We get a proton. You get an electron, and then we get an and then we get an electron neutrino here. So this is our beta minus decay. So as you can see here, your A number is going to stay the same, no change, but your Z number is going to gain 1, and then your N number is going to lose 1. So yeah, that's interesting there. So this will actually gain an atomic number here, and will actually appear to increase an atomic number. So I'm going to get to an example on that in a second. Let's just go to beta plus here real quick. So beta plus, we have the opposite going on. We start with a proton, so +1. And then we get ourselves a neutron here. So you lose the positron. So then you get, so then the positive charge goes away, and then this kind of just becomes like a neutral charge. And then you get the, what's the symbol for frickin' neutrino, antimatter electron, anti-neutrino, whatever. I don't know. Hang on, I need to find that real quick. That's gonna bug me. Yeah, okay. So all I need for the anti-electron neutrino there is a little bar over the top of it. So there you go. That's the beta plus decay. So for our beta minus emission, atomic number has gone up, and over here, atomic number goes down. So let's look at an example. One isotope that we work with a good bit in my work right now is cobalt 60. Cobalt's right here. Cobalt 60 is used in like cancer treatment devices. It's a strong gamma emitter, so you can use that to focus in and kill brain cancer. So let's see, I can put this all the way up to like here. So we have cobalt, okay, that's a big O. Cobalt 60, which decays through, I want to say beta minus, into nickel 60. Yep, that's correct. Okay. So the beta minus, we gain the atomic number. So remember, we take a neutron in the nucleus, it goes to a proton, we gain an electron that gets spit out, and or just an electron neutrino. So cobalt 60, Z equals 27, then N equals 33. We get kicked up to nickel 60, so Z equals 28, and then N equals 32. Yes, that math works out. Very good. And then the same happens for beta plus, but just in the other direction. So if cobalt 60 were to beta plus, we would then get iron 60, which would have a Z of 26 and then an N of 34. So yeah, there you go. There's your alpha and beta radiation. So alpha, for our intents and purposes, least damaging radiation because it has the lowest penetrating power. However, if it gets inside you, that's when you'd start to get damage and stuff like that. So that's one of the reasons behind like the Gulf War syndrome. We'll get into that later, so stick around for that. Beta radiation is considered the medium of the three radiation types. It's got medium penetrating power and medium damage infliction. Uh, Both alpha and beta are subject to electromagnetic interactions, and so they lose their energy really quickly. They both end up in a different element once your decay has happened. You get a different element. Not necessarily the case with gamma radiation, but we'll get into that later. And yeah, so I think that's where I'm going to stop there. Thanks for watching, guys. Tune in next time. We'll cover neutral radiation. We're going to cover photons and neutrons. Not really neutrinos, because we've basically covered all there is to cover about them. They don't do anything. So neutrons and photons. And after that, I'm not sure where we're going to be going. We might be able to start talking about fission. So stick around for the future, because we're starting to get to the fun stuff. So see you guys later. Thanks for watching. Have a good one.